Alright guys, let's do 21. We have antimony pentachloride, antimony trichloride, and chlorine gas. So we're going to write the equilibrium constant expression here. So for A, we're going to do both. I'll do KC. And KC will be equal to the products, concentration of products, antimony trichloride, chlorine gas, all over antimony pentachloride. Kp equal to the pressure of SbCl3 times the pressure of Cl2 all over the pressure of SbCl5. That's it. And a lot of times you might see parentheses around, and that's if you want to do it that way. I like to do it that way. That's cool. Either way, there we go. So that's how you would do this. And everything's gas, so everything's involved in the equilibrium constant. B, you guys can pause this now, do B, C, and D real quick, and then see what you get. So hopefully you got these. And just note we have some coefficients here that are in the exponents. So you can look and make sure you get all your coefficients highlighted. I have the Q's, 4. So all those coefficients are the powers. But Kc, Kp, that's the equilibrium constant expression. So when we talk about equilibrium constant expression, as it has here, that's all equilibrium constant expression. That's all I'm looking for in 21. That's it. So let's look at 29 now. So now we have a reaction, 2 reactions, and we want to get a third reaction. So I have NO, bromine, NOBr, and then NO, N2, and O2. I got 2 Ks, they're Kps, and I want to find the equilibrium concentration, or not the equilibrium concentrations yet. We'll get there later. I want to find the equilibrium constant expression of this last reaction. So what do I have to do? Well, the first reaction, if I look, I like to do products. NOBr is a product, but there's a 2 in front of it. So I'm going to need to double. I'm going to double the first one. So if I double the first one, that means I would put a 2, make that a 1, and make that a 2, which is good. I have to square Kp. The second reaction, N2 and O2, are on the other side. So I would need to flip the second one. If I flip the second reaction, I have to invert K. So let's try this. So we're going to double the first one. And I have 2 NO gas plus Br2 gas going to 2 NOBr gas. Now that's Kp is 5.3 squared. In green, we'll flip it. So I have N2 gas plus O2 gas going to 2NO gas. Kp would be 2.1 times 10 to the 30th to negative 1. So let's add these up. Let's see what happens here. 2NO plus Br2 gas plus N2 gas plus O2 gas is going to go to 2 NOBr plus 2NO gas. That's a gas. And works out. It looks like I get it because the two NOBRs are gone. So this new K would be 5.3 squared multiplied by 2.1 times 10 to the 30th to the negative 1, which would be 1.3 times 10 to the negative 29. And there you go. So there's a manipulation of K. Let's try number 30. So we want to use the following reactions to predict the 2A going to 3D. All right, so why don't you guys try it for a second, pause this, try it, and see if you get the right answer. So hopefully you got the answer. Let's see what I'm going to do. So I have A here, I have 2A there, so what I'm going to do for the first one is double the first one and square that. And then for the last one, I think I have to flip it, which means I have to negative 1 that, invert. And so if we do that, if I double the first one, I get 2A solid going back and forth to B gas plus 2C gas, and I get K1 squared, whatever that number ends up being. In the second one, I'm going to get B gas plus 2C gas going to 3D gas, and that is K2 to the negative 1. If we add those up, the B's and C's cancel, which is wonderful. So I would get 2A solid going to, right, because B's are gone, C's are gone, to 3D gas, which is perfect. So K would equal 0.0334 squared multiplied by 2.35 times to the negative 1. So K would equal 5.04 times 10 to the negative 4 is what I got. So hopefully that's what you got as well. Number 36. Number 36. An equilibrium mixture has a reaction at a certain temperature. It has ammonia at this concentration and hydrogen sulfide at that concentration. What's the value of K? So we want to figure out Kc, the concentrations. What is the equilibrium constant expression? Kc is equal to the concentration, in this case we're using concentration because that's what the problem gives us, of NH3 times H2S. And then if you look, we have a solid here, don't we? Since that's a solid, it's not in the equilibrium constant expression. Well, now I have data here for ammonia and H2S. I have these. And we're looking for, what is the value of Kc? I'm looking for that. I can solve. So Kc would be equal to just multiplying these two numbers of ammonia was 0.278 molar and hydrogen sulfide 0.355 molar. So Kc happens to be 0.0987. And that's it for 36. We just found Kc because they are, right, the key word that we didn't highlight is an equilibrium mixture. So we're already at equilibrium at that temperature. So that's 36. 40. Now we have a new reaction with SO2Cl2 and SO2 and Cl2 gas. So in a reaction at equilibrium, that's important. We are at equilibrium. The partial pressure of SO2 is 137 torr, and Cl2 is 285 torr. What's the partial pressure of SO2Cl2? Of sulfuric chloride here, and it gives us K, Kp. Now remember, this is important. K needs to be in atmospheres. I am in torr. We have to fix that. So Kp would be equal to the pressure of SO2 times the pressure of Cl2 all over the pressure of SO2Cl2. Well, what do we know? Well, we know everything besides SO2Cl2. So K happens to be 2.91 times 10 to the third. Now, how do I get torr to atmospheres, right? So if I have 137 torr, we know that there are 760 torr per 1 atmosphere. So we're just going to divide by 760. So what I'm going to do is I'll take my 137 divided by 760, and Cl2 would be 285 divided by 760, all over the pressure of SO2Cl2. Now, it does not say what units my pressure of SO2Cl2 has to be at all. Does it have to be in torr? Does it have to be in atmosphere? I don't know. Now, if you're doing this let's say this is a homework assignment on Pearson, it might specify what you have to do. For us, it doesn't say on this example. So, if we do this example, what do we get? Well, first of all, rearranging pressure of SO2Cl2 would be equal to our 137 torr divided by 760 times our 285 torr divided by 760 all over our equilibrium constant of 2.91 times 10 to the third. And that will give us a concentration of, so this will give us a pressure of 2.32 times 10 to the negative fifth atmospheres. And if I multiply that by 760, I actually get 0.0177 torr. So that's what I get for number 40. Number 44. You have SO2Cl2 again, SO2 and Cl2. Let's talk about K. K is equal to, in this case we got concentrations, the concentration of SO2 and the concentration of Cl2 all over the concentration of SO2Cl2. So reaction mixture is made containing initial, new word here, initial concentrations of SO2Cl2 of 0.2 molar. And that's the thing is, we can only control the initial amount. We can't control anything else. At equilibrium, so there's a new term, at equilibrium, we have Cl2 is that concentration. Calculate the value of the equilibrium constant Kc. So now we have to calculate K. So we're looking for this. I only know Cl2's concentration. I don't know anything else. So I'm going to rewrite the reaction. SO2Cl2, and I have SO2 plus Cl2, and this is where we get to introduce to you the ice table. And the ice table will be something you will have to do in every chapter until the end of the course. And ice stands for initial, change, and then I'm going to put on equilibrium or end. So we have an ice table. Initially, we knew we had 0.020 molar SO2Cl2, sulfuric chloride. However, we have no products initially because we don't have products initially. Once this reaction reaches equilibrium, we now know that the concentration of Cl2 happens to be 1.2 times 10 to the negative 2 molar. And that's all we know. Well, I think we can kind of extrapolate some details from this. I know some SO2 CO2 had to react to make SO2 and CO2. We further know that it's a 1 to 1 to 1 mole ratio. So if the concentration at equilibrium of CO2 is 1.2 times 10 to the negative 2 molar, what do you think the concentration of SO2 is at equilibrium? I would say it's probably going to be 1.2 times 10 to the negative 2 molar as well, because there was no original and there's nothing else added. That means the change had to be plus 1.2 times 10 to the minus 2 molar plus 1.2 times 10 to the negative 2 molar, which means we subtract 1.2 times 10 to the negative 2 molar from SO2CO2 because that's how much reacted. So at equilibrium, 0.020 minus 1.2 times 10 to the negative 2 gives us 0.0080 molar. So now we can plug all three of these into K. We don't know what K is, but it's going to be equal to the concentration of SO2 times the concentration of Cl2 all over the concentration of SO2Cl2. And those happen to be 1.2 times 10 minus 2, 1.2 times 10 minus 2, all over 0.008. So K looks like it is 0.018 if we do that math. So that's a nice table, and that's how we solve for K here in 44. 54, another one. So 54, we get a reaction. Kc is 255, so it gives me the equilibrium constant. Kc, 255 at 1,000 Kelvin. A reaction mixture initially contains CO concentration of 0.150 molar. So CO is 0.150 and Cl2 is 0.175. The question says, what are the equilibrium concentrations of CO, CO2, and COCl2 at 1,000 Kelvin? Wow. So let's rewrite our problem here, our equation. CO plus Cl2 going to COCl2. Ice table. So the ice table, we have initially CO of 0.150 molar. Cl2 is 0.175 molar. Now my equilibrium constant expression, K, in this case it's a C, but K is equal to the concentration of COCl2 divided by the concentration of CO and the concentration of Cl2. All I know is K and the initial concentration. I don't know anything else. I don't know my equilibrium concentrations of anything. I do know that there is no product at the beginning. What happens? Well, we know some of this is going to react. Now, K is 255, so that means we're probably going to have appreciable amounts of COCl2 and CO and Cl2 in the reaction. Okay, so, what's up? What do you do? Well, we know some reacts. How much? I don't know. Well, in math class, what do we put for an unknown that can change? Or is variable. I'm going to put minus x down, and plus x, because it's 1 to 1 to 1. So we know that it's 1 to 1 to 1, the mole ratio. So xx, it's the same addition subtraction for both. So that means equilibrium here, I have 0.150 molar minus x, 0.175 molar minus x, and x molar. So now we're going to plug this into K. My value of K is 255 equals x divided by 0.150 minus x and 0.1750 minus x. And now I have to solve for x, which at this point, this is algebra. So now we're no longer doing chemistry, we're doing a little bit of algebra. So took a journey. So the first thing I'm going to do is this bottom, I'm going to bring up top. So I'm going to get 255 times, I'm going to put the brackets around this, 0.150 minus x, 0.1750 minus x equals x. Okay, what I like to do in this situation is I'm going to everything in, well, let's do the big brackets first here. So I'm going to do everything in blue first. So that's first, outers, inners, last. Right, if we do that. So I'm going to keep 255 times 0.15 times 0.175 is 0.02625 minus 0.15x minus 0.175x plus x squared equals x. Now we have to distribute the 255 to every term. And of course, we're going to add these two together. We're going to add those terms together as well. So I'm going to come up with 6.69 minus 82.88x, 82.88x plus 255x squared equals x. So then what? Get everything to one side. So I get 255 x squared minus 83.88x plus 6.69 equals 0. And now we have to solve for x. So there's multiple ways to solve for x, but I would recommend using the quadratic formula. All right, if I use the quadratic formula, what's the quadratic formula? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Well, what we have a, b, and c. So if I solve this, x will equal two answers. X equals two answers. So what are those two answers? The answers I got are 0.193 and 0.136 to 36 things. So which answer is right? I don't know. Let's look at our original conditions. Well, for x here, I have, again, 0.193 or 0.136. And if I look, 0.193 is bigger than my initial concentrations. So this one is too large. A lot of times, one will either be negative or too large. Very rarely, and I don't think I've ever given a problem where you have two answers that could be right and you have to actually put them back in. So 0.136 is X. That means we have to figure out all three concentrations. We have to figure out the concentration of CO, the concentration of Cl2, and the concentration of COCl2. Well, COCl2 is X, which is 0.136 molar. CO is 0.150 minus X. So 1.50 minus 0.136 is 0.041. And 0.175 minus 0.136 is equal to 0.039. So that's a nice table. 7. So this is a little foreshadowing. This example I use all the time. Acetic acid. All right, we have initial concentration of acetic acid is 0.210 molar. What's the equilibrium concentration of hydronium? So now we're looking only for hydronium. We have the 0.21. K, so what's my equilibrium constant expression? So K is equal to the concentration of hydronium, which we're very interested in this problem. Acetate, C2H3O2 minus, all over HC2H3O2. Okay, rewrite HC2H3O2. Okay, we don't put water in there, do we? Plus water, because water is a liquid. So I was getting lazy there, not putting my state symbols in. Don't get lazy. Getting lazy, we forget things. Ice table. So we have 0.210. 0.210. Doesn't matter. 0, 0. Change. Minus x, plus x, plus x. So at equilibrium, I have 0.210 minus x, x, and x. Plug in. So K value is 1.8 times 10 to the negative 5 equals, hydronium would be X, acetate is X, all over 0.210 minus X. Okay, well, we got to bring the bottom up. If I bring the bottom up, all right, I get 1.85 times, 1.8 times 10 to the negative 5 equal, or times 0.210 minus x equals x times x. So if we distribute the k, I get 3.78 times 10 to the minus 6 minus 1.8 times 10 to the negative 5 equals x squared. So we get 0 equals x squared plus 1.8 times 10 to the negative 5 minus 3.78 times 10 to the minus 6. If I do that, I gotta do the quadratic here, I get two answers for x, and those answers are 0.0019. I'm gonna keep 3 stick figures, I really can't, but 194, and negative 0.00195. So obviously it cannot be the negative one because it's negative. So X happens to represent, X here represents hydronium, and so X is our answer, and our answer then is concentration hydronium to 2 sig figs 0.0019 molar. Now, which technically speaking, it would be to the right sig figs. I believe it would be 0.002 molar because we only have 3 decimal points when we're subtracting. I want to point something out. If you look back at this, right, we're going to talk about the approximation. So I'm going to rewrite the K value. 1.8 times 10 to the negative 5 equals x squared all over 0.210 minus x. So what we're going to look at here in terms of approximation, is going to say I'm looking at the exponent and the value of this number. I'm looking at those two. If it's greater than 10 to the third, either way, right? So I'm looking at the whole number. If there's greater than 10 to the third difference, so if I take K and times it by 10 to the third, or divide it by 10 to the third, doesn't matter, whatever, 1,000 times difference. If it's greater than 1,000 times difference, I can approximate the change to nothing. Example, if we were going to buy cars today, right, I'm really interested in that price of the car. That's probably one of the, there's a lot of beautiful cars out there, a lot of beautiful makes and models. I'm really interested in the price. If I had $25 million in the bank just sitting there, I would care less about the price of the car, and I would get totally what I wanted. The price of the car would not even be a thought. And $25 million minus any car that I can buy from a dealer around here would still have $25 million in the bank. That's just the way, 50,000 minus 25 million minus 50,000 is 25 million, right? We wouldn't even blink at it. And so here we're looking, if it's bigger than 1,000, we can approximate this change to 0 on the bottom. We still keep this x up top. So when we approximate, I get 1.8 times 10 to the negative 5 equals x squared all over 0.210, which then goes to 3.78 times 10 to the negative 6 equals x squared. So x, if you take the square root, you get 0.001944. So if you look, even the 3 sig figs, it's the same number here as it is here. So I got the same number. So I can approximate without even doing the quadratic expression, which is quite nice. So as long as we're more than this number, K, is more than 1,000 times different than the starting point, you can approximate the change to 0. That's really nice. Last one, 58. Consider this reaction again. So we got K, we have initial concentration of SOCO2, and what's the equilibrium concentration of CO2 at 227 degrees Celsius. So K again, I like to write out the expression. Concentration of SO2, concentration of Cl2, concentration of SO2Cl2. Perfect. Reaction, SO2Cl2 gas going to SO2 gas and Cl2 gas. Ice table. So what do we have here? Well, initially I have 0.175 molar. None, or 0 and 0. None and none. Change, minus x, plus x, plus x. So at equilibrium here, I have 0.175 minus x. Can change 0.175 minus x, x and x. Bring it into my equilibrium constant expression here. K is 2.99 times 10 to the negative 7th equals, Well, it looks like x times x, or x squared, but I'll put it in parentheses. X times x all over 0.175 minus x. Now, we are 0.1, that's 10 to the negative 1, 10 to the negative 7. That's a million times smaller than 0.1. So what I can do here is approximate this change to 0. So that means I can write 2.99 times 10 to the minus 7 equals x squared over 0.175. So 2.99 times 10 to the negative 7 multiplied by 0.175 happens to be 5.23 times 10 to the negative 8. And that's going to equal x squared. Take the square root of both sides, and I get 2.29. 2.29 times 10 to the negative 4th equals x, which happens to be my Cl2 concentration. So molar, and we're done. There's examples for equilibrium, and we'll see you in next time. Take care, guys.